Engineering Extension Education of the School of Engineering, North Carolina State University presents Value Engineering with Jerry Kaufman. This is Lesson 13, Lufkin, a case study.
This is lesson number 13 of a video series in value engineering. In the previous 12 lessons, we discussed the concepts and techniques of value engineering. Today we'll focus on the application of value engineering. To do this, I've asked Mr. Ray Blakely, Manager of Engineering for Lufkin, to join me and describe a case study involving the application of VE as applied to the manufacturing process. In addition to being Manager of Engineering for Lufkin, Ray was recently recognized by the Society of American Value Engineers in being awarded a certificate for a Certified Value Specialist. It's now my pleasure to turn this segment of the program over to Mr. Ray Blakely. Ray, thank you for coming and joining me today.
Thank you, Jerry. May I take a moment to familiarize you a little bit with Lufkin. Lufkin is a producer of linear measuring instruments. We categorize them in three areas, one being a folding wood rule, which we refer to as a carpenter's rule. Number two being pocket tape, which we produce in the form of 1/4 inch wide and 1 inch wide and up to 33 feet in length. The third category being that of long tape, which we refer to as engineering, surveying, and oil gauging. Now these tapes, the long tapes, are produced in steels from 1/4 inch wide and 1/2 inch wide up to and including 300 feet long. Our operations that we perform at Lufkin fall in three categories, and that being continuous operations. We of course paint steel, we then print steel, and after printing apply a protective clear coating to allow the pocket tape or the steel tape to give some life to the user. These processes, being as they are, run continuously. Now when I mean continuously, they are set up so that when we start, we would like for them to run all day long or 24 hours without stopping. This means that they have to be designed to allow new coils of steel or raw material to be tied in as the machine is in operation. Most of these machines, of course, are multiple line operations. The paint line in particular is 12 lines. It moves at 110 feet per minute. The print machines are individual machines, but they also can move continuously. The clear coating machine, as we call it, also is a 12-line machine that moves continuous. Our material comes from a sister plant, and the material is produced, of course, in coil form. Now the coil is designed to be about 16 inches in ID and about 28 inches OD. The material itself will be about 0.005 thousandths thick. Thereby we can put approximately 6,000 feet to a coil. This coil will weigh about 90 pounds if it's 1 inch wide and the 0.005 thick material. These coils, of course, are tied into the moving systems by the use of what we call splices. And a splice is accomplished by the use of rivets. We, with a small hand punch 2 holes in the substrate or the steel line, insert 2 rivets, and the rivets are braided over. This allows us to pull the material through the process and the process to remain in continuous operation. Now, I mentioned a paint line, 12 lines wide. An incorrectly produced splice, or a splice that's done in such a way that it will catch on a pulley or some other part of the system, could break. Now when the line breaks, of course, we must stop the line. Now picture, if you will, a line that's moving 110 feet per minute, and we have to stop. When it stops, of course, there is a section of steel that is not painted. Now it's not just one section of one tape, it's 12 lines wide. So we scrap out the potential of 12 tape lines in this process. Also on the restart, the oven control is not sophisticated enough to allow the tape to be cured, So we overcure on startup. We have another situation then in which scrap is generated when the tape line has stopped. Now this same process, of course, happens when we look at either the printing method or the clear coating method. So I hope I have perhaps told you enough about the process for you to understand our need when we look at splices. The works manager for the Lufkin operation, Mr. Frank DeBose, selected this problem. In his description, this problem probably contributed approximately $500,000 per year in extra cost to the Lufkin operation. Now that's a great deal of money, but we process a great deal of tape. We figure that we paint, print, and clear coat approximately 1 million feet of steel per day. And this is the requirements, of course, to meet our customer needs, these customer needs being in the form of consumer products as described as engineering tapes, pocket tapes, or wood rules. I have told you some of the reasons behind the purpose or the process of splicing. As we discussed this problem and its probable value to Lufkin, we began to think of who in our operation could most successfully contribute to this team process of dealing with this problem. Of course, we looked at the engineering personnel, and one was selected from there. We looked at people who work with the processes themselves in the plants. Here we're talking about setup people as well as supervision, and one was selected to represent the areas there. We also considered the sister plant that produces the steel, and of course these people we felt could contribute to the initial problem. Part of the perceived problem was a result that people said the sister plant supplied us coils of steel that contained between 4 and 5 splices per coil. And we'll talk about this a little later as to how this actually was resolved. The team was formed, and of course we had about a 6-man team made up of supervision, engineering, and also supervision from the steel plant. The first day the team spent their time talking to people from the steel plant as well as management within the Lufkin plant itself. These people giving us their thoughts on exactly what the problem caused in the Lufkin operation. Broken lines in the process, of course, causing scrap, excessive cost of the tooling to produce the splices themselves in the operations, and there was many of these tools involved because they were used by people on all the operations. Also, of course, the scrap that's generated if you try to print over a splice. Obviously, we must pull these splices through the print machine. If you print over the splice, you can't sell a pocket tape with a splice in it. It must be thrown away. In some situations, the splice itself can cause damage to a print belt. And if we happen to be printing a 100-foot belt or tape, obviously that belt is scrapped, and we're talking several $100s to replace that particular part of our system. So it's felt that there was adequate reason for the team to deal with this particular problem. I might add that the previous successes of Lufkin with value engineering also was significant in the selection by Frank to attack this problem with a value engineering task team. The first day, of course, as I've said, we applied ourselves to the selection of data. We had used a little bit different approach this time than previously in that we allowed a second day for both the visiting man from the steel mill and our own people to sort of digest this data. They began to go out and look at the operations from a different light, trying to see just how it may impact, what they maybe could come up with. It was significant for the visitor from the steel mill to see the operations that must be performed throughout the process and how the steel splices would be used. This, of course, was part of the information phase, and we allowed this information to soak into each one of them. And over this 24-hour period, we found that they came back ready to go into the next phase of the operation, really chomping at the bit, really wanting to get into solving the problem. And of course, we had to back them off because we didn't want to solve the problem that quickly. The first thing we had to do was to define the problem. In this definition of the problem, we of course asked the first question, what is the problem we're here to solve? This proved to be one of the more difficult parts of the entire process, as is often the case in value engineering. People have an extremely difficult time defining the problem in such a way that it can be attacked. But in this case, their definition of the problem was to reduce the amount of splices and improve the quality of the splices as they are produced in the steel tape line. The next question, why do you consider this a problem? And of course, from their previous days strolling through our plant and looking at the operations and the results of the splices, their answer was that the present cost of scrap caused by splices is indeed excessive. And of course, the fact that it was excessive resulted in there obviously needing to be some better method of generating splices to cut down on the cost associated with them. From this, we then began to think about how we should approach this problem in our speculation process. I might add that there were several items listed as being the reasons why a solution would be necessary, and scrap was at the top of the list, but other things: reduce the cost of the product, improve the material utilization of the product, improve the manpower utilization, we would improve machine utilization, and subsequently the employee morale would go up. As often is the case in these situations, one of the reasons for solving this was to get management off of their back. But many of the things that are associated here, you see, could impact on why a solution would be very necessary here. Our first approach was to go into brainstorming, and that was to brainstorm the possible solutions to generating a splice in a tape line. And of course, here it started out with the basic system that we looked at now. This was one of the first things that came up with, but it covered the gamut of methods that one may attach two steel lines together. Probably the most sophisticated one that we talked about would be laser welding, and everything else in between was used, even to that of bolting, lacing, things of this nature that people were aware of could be used to attach or connect these tape lines together. As we talked about the brainstorming session on this, it also came out that obviously we were going to have a system that was quick in connecting these tape lines. It had to be secure, and again it was talked about how the Cooper Steel people needed a system that could be utilized in their plant also, because they were generating a lot of the splices that were in our system. As the day wore on, it became obvious that other things had to be accomplished, so part of the effort before the next session would be to check in the system itself at Lufkin. A team was put together to go out in our process floor to actually select at random skid loads of material and to separate these skids or the coils from the skids and to count the splices as they appeared in the coils. This was done overnight by a group of people on our second shift of operation, and of course they reported the next day. As we looked at the number of splices generated here, we found that at the end of our paint process, and this is the first operation we performed in our operation, each coil of steel was checked, and on the average contained 1.8 splices at the end of the paint process. And we put one in on each line, or for each coil, as we run through our paint line. This sort of, I guess, ruined the myth that we all had been working under, that the steel mill was the source, or the major source, of the splices as we encountered them. And of course, this also put the representative from the steel mill at ease as far as his function on the team itself. He, of course, began to contribute even more so when he found out that he was not the total culprit in this process. As this was studied from time, and we analyzed and went through the brainstorming portion of this and began to take away those items that we felt were really not maybe feasible, that were expensive, or that not fast enough. Realizing again that on our tape line operation, or paint line, this being the fastest operation, we had approximately 2.5 minutes in which we had to accomplish a splice. Because again, the line is moving. If we exceeded that time, then the line would stop automatically because we had to run out of the accumulated line that was in storage. The end result, our present method was found to be as economical as could be produced. And of course the obvious question then, if it's that good, what's the problem? Why are we here? Again, our analysis, or the analysis of the team, indicated that over the years, Lufkin as well as Cooper Steel had failed to maintain proper tooling for the employees to use in the splicing operation. Not only had they failed to maintain good tooling, they had failed to train operators in the proper use of the tooling. Again, these are just management processes that had sort of fallen through the cracks, if you will. A group was selected to determine ideal tooling as well as ideal methods to be used in the splicing of the tape lines. And of course, over the next 10 hours, these methods were put together and resulted in a presentation that showed basically how to put these splices together. After this, we began to look at other methods or other ways that we could reduce splices. And of course, one of those was, once the splice was put in, to take it out. And we'll talk about that a little bit later on and how this could accomplish something for us. It was also talked about how to reduce the splices that were put into steel mill. And of course, in this discussion, it again came out that the steel mill was not really the big culprit in the production of splices. That the Lufkin process itself, the three continuous operations that I've mentioned previously, were indeed the source of the major number of splices generated at Lufkin. After the first week's work, there was a 2-week recess, at which time certain members of the teams began to put together certain things that they wanted to do. This was to verify and prove the items that they wished to accomplish. These, of course, when they came back, they met with the team and presented their findings for the team to make final recommendations to management on how they would wish to handle this particular problem. We had been told going in by management that a very high cost associated with the splices was in the tooling itself. We were given figures of up to $50,000 to $60,000 involved in the tooling. Of course, we had then to research our records just to find out how many tools were being produced and what the cost of these tools were. Upon return, the team had found out that the tools did cost us about $15,000 a year. Again, based on the amount of footage that's processed, we did not feel that that was an exorbitant amount of money to be spending for this particular process. And of course, I said earlier that we have sort of waylaid the myth, if you will, that Cooper Steel is the big culprit in splice generation. We know that it does occur at Lufkin more than it does at Cooper Steel. We also were told that splices alone were costing Lufkin approximately $500,000 a year, both in the way it's spliced and in the subsequent losses that result throughout the system because of splices. We also had figures to verify this to a certain extent. The team at this point was able to verify that splices are indeed an inherent part of the operation at Lufkin. They cannot be done away with, whether we butt weld or whether we rivet. So that was not a solution to eliminate splices. They had to be there. The things that the team came upon or worked out as far as how they could reduce the cost of these splices to Lufkin took 4 areas, or they fell into 4 categories that we'd like to explain to you. We call one of them breakback. Now, to explain breakback, I mentioned at the beginning how we produce engineering, surveying, and oil gauging tapes up to 300 feet long. And of course, in the printing process, if we print over a splice and it happens to fall at the 210-foot mark, our system allowed that we threw away the entire 300-foot tape. But with a breakback system, we can go back into our inspection process and break this tape down at 200 feet. We have a perfectly good 200 feet tape to sell to the consumer. Therefore, we only scrapped 100 feet. This was looked at from all the long tapes we produced, and we were able to come up with a system that would allow breakbacks on all of them. This, of course, would result at that time in savings amounting to about $34,000 a year, just in the breakbacks at the inspection process. We also found that in the printing of these long tapes, if we would segregate reels from the paint line, It's easy at the painting situation to determine how many splices there is in a coil. And of course, if we're printing 100 feet long tape, then we don't want to use a coil that has any splices. And we were able to determine that at least 50% of the incoming stock contained no splices. So the segregation of the coils allowed us to direct this particular material to the long tapes, thereby reducing the number of splices that would result in lost tape there. This was calculated to save approximately $13,000 a year in this process. On the paint line itself, this system was designed such that we could alert people from one end of the line to the other. And we said if we will splice in at the let-off end as we put on raw material, then we can signal at the other end of the line and tell them we have spliced in a line. When that splice arrives at the other end, take it out. This is called reel to reel. In other words, one reel of stock on one end produces a reel of stock on the other end. This one operation alone, costing about $5,000 to implement, would remove from the Lufkin process approximately 35,000 splices per year. So the impact at this point becomes obvious. Now, the proper training of how to make a splice resulted in us showing that a rivet properly flattened would not easily catch on materials or operations through the painting, the printing, or the clear coating. It would not destroy belts. It was easy to calculate then that the savings here could amount to in excess of $100,000 a year, because we knew that we were spending that much in repair because of what was happening here. So we have a situation in which the total savings from this task team amounted to approximately $180,000 a year. This gives us a rate of return for the cost of the study plus the implementation was better than $10 for each $1 spent, giving us a total saving in excess of $182,000 a year. Not only was the money a good part of what we could say was savings from this, but in the process we established a new rapport with our steel mill. Up until that time there had been some problems, maybe personality-wise, but the representative that we had included on our task team was then able to report back to his supervision that indeed we were interested, that we were working together. So there's been a new era, if you will, of communication established between the Lufkin plant and its steel supplier. I'd like to thank you this afternoon for allowing me the time to discuss this particular task team with you. And are there any questions? Yes, Jerry.
Ray, I know you've handled a number of studies throughout the year. Can you quickly describe one or two other subjects that you got involved in with value engineering at Lufkin, other than the tapes itself?
Of course, Jerry. The first one that comes to mind deals with the engineering, surveying, and oil gauging tapes. This was one of the first teams, you might recall, that we worked on together, in which we were dealing with the rationalization of the tape lines. We found that we were producing approximately 60 tape lines. We were also storing these tape lines in about 17 different styles of reels or storage cases. The rationalization process that we went through reduced the frames produced to 7. It also reduced the tape lines produced to 34. This was so drastic, of course, that marketing to a degree had some problem going the full amount. But since that time, they have seen the wisdom of that, and we are pursuing that rationalization process.
Another question, Ray. Evidently, the cost reduction impact of value engineering is almost obvious. Can you describe what you believe are some other peripheral or non-measurable benefits that can be derived from the use of the value engineering task teams or the study itself?
I believe in our instance it has brought about an improved communication between the operating departments of the manufacturing facility. By that I mean between manufacturing and engineering. It allows people from the manufacturing process or the manufacturing operation to see some of the engineering problems involved. Also, by including marketing people, they are all of a sudden aware of just what happens in the market, in the manufacturing process itself. They're so attuned to the consumer and what they think the consumer wants that they lose sight of what it takes in the manufacturing process to produce what the consumer desires. So we have realized greatly enhanced communication processes throughout our organization by involving people in the value engineering techniques. Also, we are seeing people thinking differently, particularly in the engineering and in the supervision process itself. As they encounter problems, it's no longer call someone. They begin to think now in alternative ways that it can be accomplished. This has been most evident to us in our formal cost reduction program itself, in that we have seen significant increases in the dollar savings that have been reported through this program.
I know that you certainly, in the study you're describing, increased the quality of a product. Is that a general rule? How is quality affected generally by the use of value engineering?
We have found that by the use of value engineering, we're able to enhance the quality and at the same time lower the cost. It has been perhaps part of the premise at Lufkin that in order to produce a quality product, it had to be expensive. But we have found that we can, such as in the splicing operation, just by implementing what should be good management techniques and supervisory procedures, we have improved the quality of the product through our plant by reducing its cost.
Well, you mentioned good management procedures, Ray. Is value engineering at Lufkin a separate effort, or is it integrated into the general management systems of Lufkin itself?
I would like to say that it's both, but at present it's more of a separate entity. I think over the years, as management is aware of its impact, that it will become more of the management process. It's taking place slowly. I don't know exactly how to explain this fact that they don't start immediately and everything go through the value engineering process, except that it's difficult to break the old habits. Solve the problem or put out the fire, if you will. And oftentimes, that's the reason I think it's difficult in value engineering teams to define the problem. We're not often taught to define the problem, just get the symptom out of the way.
Who is now, or who do you believe should be responsible for value engineering at Lufkin?
I think it should be the responsibility of the engineering function.
Do you have any future plans for value engineering in '85? Or that you care to talk?
Well, none that I care to talk about. I can say that we have a program going on right now we're using value engineering techniques, and we're again looking at the process involved in the long tape area. So it is being utilized in our operation.
And one last question, Ray, and then I'll let you go. For those people who are watching you that do not have a value engineering effort, what words would you care to leave them with?
Get started right away, but you need to get your management in support of you. I guess what I'm saying is this. My experience with value engineering has been that the results from value engineering task teams, properly assembled and properly directed, can be so dramatic that staff people who are not involved, and I'm talking about immediate involvement on the team, can at times be embarrassed. I have had situations in the Lufkin plant early in the VE effort in which the engineering staff itself felt that they were being bypassed in the solution of problems, that they felt were their problems. We have seen situations in which I think management has in effect been embarrassed. We find that the people that we select on the teams are very capable of solving the problem, which tells us that management does not have to have all the answers. Management needs to be willing to ask the people. And we're getting that way. We're learning to depend upon our people who are the closest to the problem. They always have the best answers, or at least we found that they have.
Close.
Again, thank you for this opportunity, and good luck in your value engineering efforts.